students, in this video we are going to talk about non-homogeneous wave equations. Yes, so initially we have looked at homogeneous wave equation in bounded domain. So essentially the space domain is between 0 and L. For that thing we have used separation of variable and solved the equation. Okay, now we are going to look at a problem which is non-homogeneous. So what does that mean? It means it looks like this: ut minus c squared uxx. C is constant, right? Now we have already discussed about it. And this a star of xt, this is how we are writing it here. And I will put the conditions here. First of all, the initial conditions are u at the point x0 equals to f of x, and ut at the point x0 is g of x. Okay, so those two are initial conditions. You remember in the last video we talked about D'Alembert formula, and we just use these two conditions. We did not use any boundary condition for that because the problem was actually posed in whole of R. Yes. Okay. So here also we are just assuming that the problem is posed in xt, which is in R cross. So x is in R, right? 0, infinity. This is the domain here. So essentially the D'Alembert's part is if you have a problem which is in the whole space R, see, time is always between 0 and infinity. So that's not the issue. The problem is this: when your x variable, the one dimension, and we are talking about one dimensional wave equation, right? So when x is, let's say, between 0 and L, yes, and let's say t, if we can fix it between 0 and some capital T, yeah, some capital T, can be million, billion, some number. So in this x of t, that will be in a rectangle, and of course we can find out how to, using separation of variable, we can solve the problem. Now the thing is this: let's say x is over the whole domain R, right? And in that case, what happens is this: we want to look at the homogeneous problem. So what do we do? Okay, first of all, we need to simplify this thing. Yes. Okay, how do I do it? So let's do a coordinate change. So by a coordinate change, and this I want you to check this, very easy. Yeah, nothing special is there. Coordinate change or transformation, whatever you want to call it. Transformation. So what is the transformation? So basically I don't want to deal with the c. You understand? Yeah. So what I will do is we'll just replace y equals to ct. Yeah. If we replace it, you can understand that there will be an extra c here, so it will get cancelled. So basically c square, that part won't be there, right? And there will be c here actually. Okay. So what we have is, see, in this case we will have uxx minus, I will write it down what exactly we will have there, uyy equals to h of xt. Clear? Okay. And this about the data, yeah, u of x0, that will remain unchanged, right? It is f of x, and ut of x0 is g of x. G of x. Is this okay? And here, see, what is h and g, where h of xy is nothing but minus h star by c square, and g of x is g star by c. Is it okay? So this is just a change of variable. What we are doing is we are just writing the L of u part, the operator part, independent of any c. And we are pushing the c on the other side, that is. Okay. One second. This is f star and this is g star. Okay. Fine. Now we need to solve this problem. Yeah. What do you do? See, let's say that maybe I can draw it here. Okay. Let's say that the point P0 is, we start with the point P0. Okay. So this is given by x0, y0. This is some point, and in this plane, right? And you see, this is the plane which we are interested in, the upper half plane, not the lower half plane, right? Okay. And you see, let's say that take the perpendicular to this thing, P0, perpendicular which falls on x-axis. Let's just call it u0. Clear? So u0, what is the coordinate? It will be x0 and 0. Is it okay? Right. So you remember there is this characteristics, right, for this thing. What are the characteristic curves? Characteristic curves are given by curves R x plus minus y equals to constants. If you remember, we talked about this thing when we were talking about the canonical form. We have dy dx equals to minus b, that particular term, right? So if you just look at this, if you compute it, it is basically x plus minus y. If you have c, it is x plus minus ct essentially. Yeah. Okay, and based on that also we actually deduce the dependence. I mean, you remember the interval of domain of dependence, right? Okay, so we are going to use that fact. See, the thing is, these two characteristics, huh? I mean, and if you want to draw these two characteristics through the point P naught, huh? See, they will intersect the x-axis, right? X-axis they will intersect, and let's just call it here, huh? Somewhere. I'm not writing properly, but let's just say that it will intersect at the point P1, and of course you can see that that will be x1 minus y1 and 0, and P2. This is P2. P2 will be x naught plus y naught and 0. Sorry, plus y naught and 0. Yeah. So you have this particular thing. Those two characteristics, they will intersect here. Okay. Right. So now the thing is this. See, so this actually forms a triangle, if you can think of it like this. See, you remember when we talked about this domain of dependence, we said that this point x naught y naught, it basically, you see, if you want to compute the function, not for this problem, for the homogeneous problem, that is, yeah. So we only need to find out what f does at those 2 points and what g does in the interior, right? Yeah, so we are going to use that fact. So essentially what we have is this. So this, in this interval, yeah, let's see what is happening. Okay, so you see, this equation is satisfied in this equation. Maybe I can write it, this equation as 1, this is as 2. Yeah. Okay, so from 1, what do you get? From 1, if you integrate 1, okay, what we get is double integral over r uxx minus uyy, okay, d of r. This is nothing but double integral over r h of xy d of r. Clear? Okay, we are just taking this thing and we are just integrating it both sides. Clear? Now once we do that, we can use Green's theorem here, right? So using Green's theorem, what do you have? In a plane, you can use Green's theorem. So double integral over r, this is over a region, right? But we do not have to integrate it over the region. We can just do it on the boundary of it. So uxx minus uyy d of r, which is dx dy essentially. So this is integral, the line integral over b. Okay, I will tell you what b is basically the boundary of the region, right? So it is ux dy plus uy dx. Is this okay? And what is b? So where b is the boundary of the, so basically, you know, this thing, this line, let's just call this thing as b1, b2 and this one. Let's just call that. Okay, so here b is b1 union b2 union b. So those three lines essentially. Clear? Okay, right. So now integral over b3. Let's just do that. Ux dy plus uy dx. What happens to this particular term? This is, if you think about it, essentially what is the change in y in this direction? There is no change in y, right? See, in b3 we are just doing it on the x-axis. So basically there is no change in y, right? The y coordinate part doesn't change. So essentially dy part is basically your 0. So this becomes uy dx. And where is x varying from? X is varying from x1 minus y0 to x0 plus y0, right? What is x1? 1 second. I'm sorry. This is not x1. This is x0, right? Okay, somehow. Okay, 1 second. This should be x0 minus y0 and 0. Okay. So this will be x0 minus y0 to x0 plus y0. Clear? Okay. What happens to b1? Let's say ux dy plus duy dx. I hope you know how to calculate the line integrals, right? We are going to use that for a while. Integral over b1, okay, minus ux, and then dx, okay, minus uy, and then dy. Is this okay? We're just writing it down because of this particular, parameterize this form, right? In b1, you just parameterize b1, and based on that, this is what you are going to get. So this, if you want to write it, this will actually give you u at the point x naught plus y naught times at the evaluated at 0 minus u evaluated at x naught y naught. This is okay. It's just a calculation. I'm just putting everything together. That's what we are getting. And integral over p2, again ux dy, okay, plus uy dx. Okay, these things I am not explicitly calculating these things, so you have to check this part. Also, you have to check this part. So this is integral over b1. Ux, this is ux becomes ux, and dy becomes in that b2, right? In b2, dx is dy becomes dx, okay, dx plus uy dy. Okay, okay. So this, if you calculate it, it becomes u at the point x naught minus y naught 0 minus u at the point x naught y naught. Yes. If you put everything together, what you get is therefore integral over b is ux dy plus uy dx. This is minus 2 times u x naught y naught plus u x naught minus y naught evaluated at the point 0 plus u x naught plus y naught evaluated at the point 0 plus x naught minus y naught to x naught plus y naught uy dx. Yeah. So if we combine all of these three together, what do you get is this. See, what I'm trying to suggest is this thing, and this thing, right? If we combine everything, yes, that's what we are going to get. So now you see this equation is there, this equation, yes. So this right hand, left hand side, that is what we calculated. So essentially, in double integral over r h of xy dx dy is essentially that. Yeah. So if you combine everything together, what you get is u of x naught y naught. Again, this is half u of x naught plus y naught at the point 0 plus u of x naught minus y naught at 0. Yes. Okay. Plus half x naught minus y naught, x naught plus y naught u y dx minus half double integral over r h of xy d of r. Is it okay? So you see, we put all of this together. So essentially, this is equals to this particular term, right? So we just rearranged it and put it together. So that's what you are going to get. Yes. Now you see, x naught and y naught is essentially arbitrary, right? And there is this change of variable y equals to c of t. So if you put everything together in terms of the original variable, so in terms of the original variable, what do you get? Well, let's see. We get u of xt. Okay, this is nothing but half of f of x plus ct plus f of x minus ct plus 1 by 2c x minus ct to x plus ct, and then g star of tau. Okay, t tau. Why g star? Because this is g, right? Yes, uy, you remember? See, uy, the boundary condition, so ut is g star. And so if you replace it, you see uy, this will be uy, uy will be g. So you see, if you put that part here, that becomes g star. So minus half double integral over r h of xy and then d of r. I hope this is clear. Yes. Okay. Now let me just give you a very simple example of how to work out this sort of problem. So let's see, you have this problem uxx minus uyy equals to 1, u at the point x0 equals to sine x, and uy at the point x0 equals to x. Yes. Now we need to know that if we can solve this problem or not. So we use this formula, right? See, what are the characteristics here? This is like x plus y, x minus y, right? So you see the characteristic, therefore the characteristics here, so we want to solve it. Characteristic curves are x plus y equals to constant, and it passes through x naught, y naught. So we want to find the value at the point x naught, y naught, let's just say. So it is essentially x naught plus y naught. Yes. And we also have x minus y equals to constant, and that passes through x naught, y naught. So essentially that will be x naught minus y. Clear? Okay. So what is u of x naught, y naught? Therefore, u at the point x naught comma y naught, this is nothing but half times sine of x naught plus y naught plus sine of x naught minus y naught. Okay, plus half times, I'm just putting it in the formula, right? This formula, you see, f is sine here, so I'm just putting there, and then g star in this case is x, and this is h we already have, which is 1. Yeah, so we'll just put that part here. So this is x naught minus y naught to x naught plus y naught, and then that is tau d tau, okay, minus half, this is integral over this r region, right? See, integral over this region. Yeah, and that region, what is the region in this case? So this is the thing, you have to draw this part here. You see that region x naught y naught, if this is the point we are interested in, x naught y naught, that region is x naught minus y naught 0 and x naught plus y naught 0. So basically the triangle which is this is your r. Yeah, so you have to integrate over this. Okay, so first of all, you see what is h? H is 1, and then dx dy. What is dx? Dx is it, so it varies from, you see, one second. X varies. So if you fix a y essentially, so x varies between y plus x naught minus y naught, okay, and minus y plus x naught plus y naught, okay, and then your y varies between 0 to y naught, right? So it is between 0 to y naught. Okay, I hope this is clear. See, for a fixed y, so let's say if you fix a y here, so your x is varying between here, I mean from here to here, right? From this point to this point. So this point for an arbitrary y, so let's say this point is given by y, so it is y minus y plus x naught plus y, y plus x naught minus y naught, and then this point is minus y plus x naught plus y naught. So we have that. Okay, so now if you put everything together after the calculation, so please do this calculation yourself. This is sine of x naught plus y naught plus sine of x naught minus y naught. Okay, done. And then plus from here you do see that it's nothing but x naught y naught, and then here it is y naught square. So this you have to check it yourself. Please check. This is very easy. It's not very difficult. So you have to check it yourself. So please check this, and then we are done. I hope you have understood how this double integral works, right? Huh? Okay, let me just give you another, just some hints. Hints. See this line. What is this line? This line is given by x minus y equals to x naught plus y naught, right? And this line is given by x plus y equals to x naught plus y naught. Yeah. So you see, if I fix a y, for a fixed y, x is changing. So x is changing from where? From, you see, x is in this case is y plus x naught plus y naught. See, this is y plus x naught plus y naught. And here on this line, again, y is fixed, x is changing. So if y is fixed, I can take y this side. So x lies between minus y plus x naught plus y naught. See, minus y. So first of all, x lies there. So for a fixed y, this is true. Now you see, we are taking y from 0 to this line. We are taking y from 0 to here. So once you do that, you have your answer. Yeah, I hope this is clear. So please check this part yourself. I think it will be very beneficial for you. Right. So now that we know all that, what I will do is this one small details I want to fix here, that what is the physical interpretation of this particular thing. Yeah, because we talked about the physical interpretation of Laplacian, I remember. So we will also do it here, interpretation. I don't think I did it, but anyways, let's just do it again. Okay, even if we did. Okay, so what we'll do is this. It's just one dimensional wave equation, 1D wave equation. So these sort of things are also available for 2D, 3D wave equations. All of those are there. But for now, we're just looking at 1D wave equation. Okay. So you remember we talked about the string and all. So essentially, let's say u of xt. Yeah, and that represents the displacement. The displacement. Okay. In some direction x, okay, at time t greater than equal 0. So essentially at some time t, you just look at some displacement, some let's say a membrane or a string, something. In one dimension you can think of a string. Yeah, and let's say initially at time t equals to 0, it has been displaced from here to here. Yeah. Okay. Now the thing is, you see, let's say that we start with a V, which is a sub-region. Okay, a subset, if you can think of it like this, of U. U is a open connected set. What do I mean by this? See, all of these, x is in R, right? You can think of it as an R or in some domain. Yeah, but let's just say stick with R. Okay, let's just stick with the domain. It will be clear. Otherwise, in R you may get confused. So let's say x is in U. Yeah, and t is given to be greater than equal 0. So this is some domain. X is in U, right? So U is some interval. Let's say A B. This is U. This is A B. So since this is an interval, connectedness is always given. So this is U, which is open interval. Open interval in R. We are doing it in R. Is it okay? And V is some sub-region. So basically V is some set here. T is positive. That is given. Okay. So V is a region in U. What is U? U is the x variable. U is where x is varying, right? So you see, the thing is the acceleration. Then the acceleration. Okay. Within V is t square dt square. You remember the acceleration is given by the second derivative of with respect to time, and then it is integral over v u dx. Yes, and then that is equals to integral over v u dt dx. Yes. Okay. So what we have is this, and this is equals to this, right? You can just write it. Take the integral inside, and the net contact force. So these particular laws, they are coming from physics, right? So what do you have is that net contact force around the boundary is F dot gamma ds. Here F is the force acting on V. So here F is the force acting on V, okay, through del V, okay, and mass density, we will take it to be unity, is unity. Here, this is what we take. Okay, now see if this is the net force, you understand, so that is acting on the subregion V, and how is it acting? Through the boundary del V. So essentially that is the force. So this is the component of the force in this direction essentially. Yeah. And the thing is, by Newton's law, what do you know? That the mass times acceleration is the net force. So essentially this net force is mass times acceleration. So what does that mean? It means Newton's law. Newton's law, that will actually give us that integral over V utt dx is equals to integral over del V F dot gamma ds. Okay, right? Mass times acceleration, the mass density is 1, so essentially mass times acceleration is net force. We are assuming mass to be unity. Of course, if it is not, this will be some constant times, right? But let's just forget about that part. So it is this. Okay, now you see, this is this identity. What happens is this, this V is an any region in U, yes, and so utt, okay, equals to minus divergence of F. Here, this is what? This is by Gauss divergence theorem, divergence of F, right? So this is divergence. So by Gauss divergence theorem, this is actually integral over V divergence of F ds. Okay, so essentially it means, and since this holds for all V, utt equals to minus divergence of F. Yes. Now you see, for elastic bodies, actually what happens is this, for elastic bodies. So here I have used Gauss divergence. Okay, for elastic bodies, what do you have? You have that F is basically, F is the function of the displacement gradient, and that is given by d of u. Okay, so essentially utt plus divergence of function of gradient u equals to 0. Clear? Now for small gradient u, so for small change in u, small change in displacement, okay, see, if you linearize this, f of del u works like minus a times du. Is it okay? And therefore, and hence, I hope this is clear. See, this is the idea of derivative, right? That in a small neighborhood of some point, if the function is differentiable, so you can approximate it using your linear component of it, right? So essentially, that's the idea which we are using for small displacement. Yeah, what we have is, you can have a linearization and you can write it like this, that it becomes utt minus a times Laplacian of u. This is equals to, this is okay. This is the wave. This is the wave equation interpretation. Here you see, u is the displacement, ut is the velocity at the time t equals to 0. Okay, so those are the initial data. So the initial data, maybe I can write it here, initial data or initial condition, whatever you want to call it. Initial data, you see, u is the displacement at t equals to 0. Okay, and ut is the initial velocity, right? So we'll just write down the velocity at t equals to 0. Why initial? Because we are starting point at t equals to 0. Clear? Okay, so those are the things. This is a physical interpretation. Now, the last part which I want to do, and this is the very important property of uniqueness. See, you remember that we talked about existence of solution, right? In this part, you see, if it is in R, we actually talked about how to find how to find a solution for a non-homogeneous problem, right? Okay, in R. So in R, X is in R. What do you know? We know that for a homogeneous problem, you have D'Alembert's formula, D'Alembert's, right? And for a non-homogeneous problem, what do we have? This particular thing which we did right now. This we did. Okay. Now, let's say X is in 0L, bounded domain. Of course, T is greater than 0 in all the cases. So in that case, what do? You use separation of variable, and for the homogeneous problem also, you use separation of variable, but in a slightly different way. These I will explain to you in which way. Yeah, because the way which I will show you to solve the inhomogeneous problem using separation of variable method, this can be used even for harmonic functions or the heat equation also. Yeah. Okay. So how do I go about the now? The thing is, and we have also looked at that using D'Alembert's formula. We have looked at whether the solution depends continuously on the initial data or not, right? We have seen that. So now we will talk about uniqueness. So let's say that U is a bounded open interval. Okay, and look at this problem. UTT minus UXX, you can put C square, doesn't really matter, equals to F in homogeneous problem. Okay, in U cross 0 D. So I am doing it for a bounded domain. There will be a question. So let me just put it here first. U at x0. Okay. So U at x0, let's say call it G, and UT at the point x0. So initial data, this is equals to, let's say G and H, F, G, H. So this on this is U cross T equals to 0. Okay. So what is happening here? Let us see. Let's say your U is open AB. Clear? So we are looking at this interval. Okay. Not interval, but basically this region. Okay. So let's say this is your capital T. This is the region where we are interested in. Right. See, in this region, UT at the point x0, this is just called the thing as H. Right. And on the other part of, so let's say this one, and this one, on these three boundaries, U is equals to G, and here UT equals to H, only on the base, UT equals to H. So this is true in U cross open 0 T, the closure of it, minus U cross open 0 T. Is it okay? Yeah. So essentially, we are not putting any data here. We are just saying that on this line, and on this line, U is nothing but G, such that UT is H only on the boundary. Yeah. So this is what sort of problem? This is called the boundary / initial value problem. Boundary / initial value. You remember when we were talking about wave equation, we took this G to be 0 on these two boundaries. Yeah. So this is a more general problem. G to be 0 on this boundary, and here we are assuming it is some H. Here we were assumed that U is G and UT is H, right? But here we are assuming U is G on this line, UT is H on this line. But here also we have something which is non-zero. So U restricted to those two lines are non-zero. Okay. So T equals to 0. I should write it as T. Sorry, there is a mistake here. This is T. Okay. So now for this problem, so one question I want to pose here. What I am doing the theorem which I am showing is, will it be true? Will it be true if x is in R? Yeah. So this is the question which I want to you to answer. So the theorem which I am putting here is this. This is called the uniqueness theorem. So it says that there exists at most one solution. At most one solution is, if there is a solution, it has to be unique. At most one solution. And what is the solution? Of course, it is in C2. C2 of U cross close 0 T. Okay, which solves 1. Let's just call it 1. Clear? So we solve this problem. Is it okay? So I will just give you a small proof of it, and then we are going to end this video. So what is the proof? So let's say there are two solutions, U and U tilde. Okay, so if U and U tilde are two solutions, okay, then W, we can define it to be U minus U tilde. Yes, and what do you have? We have WTT minus Laplacian of W equals to 0 in U cross 0 T O closed. W equals to 0 on this set. Let's call it a gamma of T on gamma T, and WT is going to be 0 on U cross T equals to 0. It's okay. Yeah. So what we did is, if you have two solutions, since we have linear equation, all these A, F, G, H, they actually become 0 if we define U minus U tilde to be W. So for W, all of this becomes 0. Now we define something called the energy. So this is a system, right? That system has an energy. So the energy of the system, let us call it E of T at any time T. Yeah. This we define it as what is the energy? It is basically the sum of the kinetic energy and the potential energy, right? So it is essentially, and that if you want to write it mathematically, it will be half integral over U WT square and xt plus this is W prime xt. So with respect to x, maybe I can write it like this, with respect to x, xt and square of it dx. Clear? Okay, and this is for any 0 less than t less than t. So essentially what am I doing is this, I am just writing down the total energy of the system in terms of the potential and the kinetic energy. If this is the case, therefore if you take the derivative with respect to t of this function, then that will give us, and then do integration by parts. Essentially it becomes integral over U, and U is some interval a b. I'm not writing it. If you want, you can just do it. Okay, so this becomes WT, right? And then there is another derivative chain rule. So WTT plus W x, and then one second, this will be D. Okay, so W x of T and then dx. Okay, I'm just taking this with the derivative with respect to t. Yeah, so that's what. See, if you take the derivative with respect to t, this is what we are going to get. That 2 part, this will go out, so this 2 and 2 gets cancelled. That's why we are not writing it. Okay, so this becomes WT and W. I made a small mistake somewhere. No, WT. It's okay. So here what we will do is we'll use a change. So this is I will use integration by parts here. Integration by parts here. If I use integration by parts, this becomes WTT minus WXX. And on the boundary W is 0, so the boundary terms won't be there. So it becomes only D of x. Now you see WTT minus WXX is 0. So basically this is 0. Therefore what it is showing is the energy with respect to time t actually is essentially 0, right? So this becomes that E of t equals to E of 0 is equals to 0. So basically E prime t 0 means energy is constant. That's what we know, that for a system the energy is constant. So this is the mathematical proof of it. Yeah. So here since E prime t is 0, it means that E is constant. So at any time t, E of t is equals to E of 0, which is 0, right? And you see W of t equals to W of x equals to 0. It means the W is constant, right? So that will imply W is constant, is constant. But we are given that W is equals to 0. You see, W is equals to 0 at U cross t equals to 0, right? So that will actually imply that W is equals to U minus U delta, okay, which is equivalent to 0 in U cross 0 t closed. Okay, therefore U has to be equivalent to U delta in U cross 0 t closed. So uniqueness. Is this okay? Yeah. So this is how you find uniqueness. Okay, so with this, we are going to wrap up the wave equation. There are some parts of it, how to solve non-homogeneous problem using the separation of variable and all. This we will do it in a single lecture, where I will show you a technique which can be used for any wave equation, heat equation, or Laplace equation. Okay, right. So with this, I am going to end this video. Thank you.